Okay, our first question of the day is looking at nomenclature, and the initial question was actually just a straightforward one, but we'll try and work through all of this so we can piece kind of all of it together. This is one that I would try and color code a whole bunch on, and we'll see how far I get because I'm going to run out of colors because this is a wicked long name. So, when you start with nomenclature, where do you start? The longest carbon chain, which kind of painfully is somewhere in the middle end. So there's our pent. Okay. Arguably, the an is relevant because the an is in reference to the hybridization of our carbons all the way through that kind of backbone. Okay. Which we're going to hit kind of a pseudo exception to that in a second. So we're looking at carbon 1, 2, 3, 4, 5. We've got 5 carbons, all showing sp3 hybridized. That's our an, our alkane, sp3 hybridization. Where should we move to next? Finish out your core structure. So that core structure is then going to be dropping all the way to the end where it says amide. So you now need to know what an amide functional group is. Okay. As far as nomenclature goes, I honestly don't remember what the nomenclature video that I made you watch goes through and does, but there should be a summary within that video of here's all the kind of appendages, if you will, that belong to it. And I'll pull that up in a little bit, but since we're drawing it, we can't do that. Does anybody know what the amide functional group is? Nitrogen is involved. It is not a single nitrogen because that would then be an amine, not amide. Duh. D versus N.
That's where you lose me. I have no idea.
Okay. And if you're like, I don't think I learned that, you probably haven't learned that. That's second semester. It's a second semester functional group is the amide. Okay. We aren't talking about its chemical reactivity yet. We will see that later in the semester, significantly later. Okay. The amide is a carbonyl connected to a nitrogen. Okay. So we're really looking at 3 atoms, carbon, oxygen, and nitrogen, which then means I need to append that somewhere within the structure. Formally, we should append that at position 1. Since we haven't established a position 1, it doesn't really matter where we place it, either on the left or the right. I would argue test-taking strategies. We don't want students accidentally getting the answer right by starting with carbon number 1 on the left because we read left to right. So for me personally, I would immediately reflex to putting it on the far right. I think I got my lefts and rights confused there in that statement. But in any case, I would place it there as opposed to on the left. Okay? We now have a sequence of substituents that we have to go through and process. Okay? Within those substituents, it doesn't really matter where we start. We just know that those substituents need to appear. So where would you like to start? 2, okay. So we could start, we're starting with that 2 as a reference. That 2 is a locator. So that's telling us where to place the substituent. What is the substituent we're talking about? Okay. The statement of dimethyl isn't horrible, but it is wrong. That's not the substituent. The di is a different thing. The di is the amount. So we've got a locator. I know it's really small. And an amount. The substituent is methyl. Okay. I wish I could say, and it's just honestly my ignorance, that if you're seeing those Greek prefixes, that's always an amount. I think it is, but I'm honestly not positive on that. Okay. So at this point, what we're saying is we have a substituent of a methyl. So what is a methyl?
CH3.
I accept that. I would go with just 1 carbon, but CH3 works. Okay. And now we need to know the locator. We identified at least one of those locators being 2. Okay. This is where it's important to number out. We started the amide, since it's our primary functional group, at position 1. 1, 2, 3, 4, 5. At position 2, I need to drop a methyl group. Okay? If I want, I can get specific and call it a CH3. I'm okay with that. Okay? We do have a di. That die is saying an amount, saying that we have 2 methyl groups. Okay? It is not saying that we have 2 methyl groups at position 2. The locator has to tell me where each of those methyl groups is located. The 2 specifies one of them. The other locator is that N. Those are both locators separated by a comma, and then we've got the dashes on either side. Okay? So what the heck is an N locator? As a locator, it must be something in our drawing. It's the nitrogen. What we're saying is that nitrogen has a CH3 connected to it. That's the other substituent. Okay? And if you do find yourself saying, what? I don't understand why. It's nomenclature. Deal with it. That's the rule. That's what it means. So that capital N in this context is referencing nitrogen. So we would go through and look at our structure, find the nitrogen, place our substituent at that locator. Okay? Have we finished our name? Nope, because we've got another substituent. What's the other substituent? Except that pronunciation also, I'd call it phenyl, but that's okay. We have a phenyl, we have an amount, and then we have, again, 2 locators. So we'd go back to trying to place those groups. What does a phenyl look like? Okay, cool. That just means you got to review your nomenclature. A phenyl is just a benzene ring. We can't call it benzene because benzene is now saying it's the root name. We've already, as I erase half my structure, we've already established the root name is the pentanamide. So a phenyl is just saying there is a ring connected to my root structure. Okay, so that's position 3. Where's position N? The nitrogen, and I can draw a phenyl also connected to the nitrogen. Okay. Have I finished my name yet? No. Oh, hell. What else do we have to deal with? We also have to manipulate chirality with the 2R3S. Okay. Do you want me to do that? Sure. So 2R3S, we'd start, it doesn't really matter. I'm going to pick position 2. Okay, the first thing I would go out to would be carbon, carbon, and then carbon from that position 2. I can't tell a difference between those, so I go out 1 atom further away. Okay? For the top carbon, I'd go out to a hydrogen. Okay? For the 3 position carbon, I'd go out to carbons. For the 1 position, I would go out to an oxygen. Oxygen takes priority over carbon and hydrogen, therefore my 1 position is labeled as 1. Those 1s, while they are both called 1, mean very different things. One of my 1s is the position number in the chain. One of those 1s is the priority with regards to the position 2's chirality. Ish? Ish enough. Okay? For the other 2, the top one went out to a hydrogen, the other one went out to carbon. Carbon is a higher priority than our hydrogen, which then means we've got 2 and 3. Okay. Officially, there's a 4. Where's the 4? There's an implied hydrogen. Because this is smart work, we must show that hydrogen at any chiral position because we have to be explicit behind it so that it can grade us. Okay? And for our 2 position, we wanted to go R, we wanted clockwise. So we need to be going 1 to 2 to 3 in a clockwise fashion with our lowest priority aimed away from us. My easiest approach would be to always start with the 4 aimed away from us and hope for the best. Okay? 1 to 2 to 3, am I going clockwise based off of my green numbers? Yeah, that's exactly what I wanted. That's R. which means my CH3 must be wedged. Okay. Questions? Okay. Now I can repackage this. Since it doesn't look like I have any orange on my drawing, I'll now go through and do the orange for my other chiral atom, position 3. I'm going out to carbon, carbon, oh God, carbon, and my hydrogen. I would again, actually I'm not going to draw that yet, and we'll see why in a second. Okay, but our hydrogen. I see no difference between carbons, so I have to go out one further to an atom. Okay, my labeled position 4 carbon goes out to 2 hydrogens and a carbon. My phenyl ring goes out to no hydrogens. It's only going out to carbons. This is a scenario with the double bond that we have to add a phantom carbon, so that orange bottom carbon on our phenyl is going out to 3 carbons for nomenclature's sake. Okay. It comes out okay. The label 2 position goes out to 2 carbons and a hydrogen. Okay. 3 carbons is going to take priority. That one's going to get a 1. Okay. Comparing position 4 and 2, I went out to 1. For position 4, I went out to 1 carbon and 2 hydrogens. For position 2, I went out to 2 carbons and 1 hydrogen. That means my position 2 is my higher priority. That gets a 2, that gets a 3. So far, so good? Silence is kind of spooky. Okay, a head shake, that's fine. Okay, this is position 3. I'm looking for S. I want to go counterclockwise. I've got my 1, 2, and 3. I'm going to again guess that I want my hydrogen to be dashed going away because it makes me easier for me to go through interpret. Okay, and if I make that dashed, I go from 1 to 2 to 3. What direction am I turning? Counterclockwise, which is S. So that's good. That means position 1 should be a wedge also. Kind of, sort of? Okay. That worked out too cleanly, so let's screw that up a little bit. And let's say it wasn't 3S, it was 3R. I got to backtrack out of that first a little bit. Okay, good. It wasn't 3S, it was 3R. I started by saying the hydrogen was dashed away from me. Okay? And if I go through and do that, that's 1, 2, 3, that looks like it's moving S. If I want 3R, I'm not looking at the structure right. Which means what do? Instead of the hydrogen being dashed, the hydrogen must be wedged. So I start with the easiest guess for me. If I'm wrong, flip it. That's all I got to do. There's a sneeze in there. Does that make sense? Oh, that's not helping. Is that good enough?
Yes.
Hi. I will try to periodically ask more nomenclature questions kind of throughout the semester. I hate it if you couldn't tell already. I don't think it's particularly useful. And I am very unpopular for that decision. But there's plenty of things that I'm unpopular for, so might as well add that to it. It's not the least of which, right? Thanks, Josie, for that affirmative acknowledgement. Which chapter was it again, Ivan?
Chapter 24, six-click oxidative. The question 5.
And we're going to talk a little bit about kind of the opposite direction of this in a second. Well, we'll see where questions come from. So what we're being asked for is what is the starting material? Okay, blanket statement at this point. Really, all we do the entire semester is here's another reagent. This is what it does. This is how it does it. Okay, and then when you're like, ooh, I think, and as soon as you say I think, I go, here's another reagent. Okay, and you look at me a little cross-eyed, and then you start to go, okay, and I say, here's another reagent. And then I don't even let you start to acknowledge that you've even seen new reagents. You just get more and more stuff. Okay, that's what second semester is. It's just tons of stuff being thrown at you. Okay, what we're trying to look for as much as possible is the patterns within that. Okay, what you are responsible for is not just what the reagent produces, but also where it came from. So you have to acknowledge all of those individual pieces, and that is a challenge. This particular reagent is one that is not talked about in the lecture videos because I want you to dig it up in the textbook. I cannot cover all of the reagents. Sometimes those reagents are things that you can reason through. The methyl lithium that we talked about last week, great, you should be able to reason through that. Some of them, like this, you aren't going to be able to reason through. Okay, so why am I asking questions? I know there's a high likelihood of it possibly showing up on a test. Let's provide you the impetus to go back and take a look at the textbook and start referencing what the reagent is. Okay? This reagent itself is known as periodate. Okay? So what you're responsible for doing is looking up to see what periodate does. Okay? Any guesses what periodate does?
It makes the aldehyde.
I'm going to say no.
Dissociates?
No. Neither of you technically wrong, but no.
An aldehyde is the hydrogen, carbon, double.
I'm not disputing that you have an aldehyde there. You're correct about that. It cyclically oxidizes. Okay? So what you should be looking up is the cyclic oxidation reactions. So you should navigate to the cyclic oxidative chapter, which is chapter 24. Maybe slightly different. I might be off by 1 or 2 chapters because of the addition switch on us. It might still be 24. And you would look up what periodate does. Okay? Since we are talking about cyclic oxidation, okay, what it does is it reacts with syn diols. Why should they be syn? It's in the cyclic oxidative system for a reason. They have to be syn because what periodate does is it's going to coordinate through some nasty complex system involving its oxygens and those oxygens to do some weird, crazy chemistry where a bunch of electrons shuttle around in this goofy-looking cyclic transition state. And if you're like, I don't see the arrow, I don't care, don't look at the arrow. It's the cyclic oxidative system, and what it produces, that's my cyclic oxidative. What was the last word? No one looked, so that was okay. That was probably a bad gesture, but it was funny. Cleavage.
Oh, that makes sense. I was like, what the hell are you on?
Cyclic oxidative cleavage. So we have to break something within this structure. If we're breaking the oxygen-hydrogen bonds, that's acid-base. That doesn't need anything fancy for cleavage. Oxygen-carbon, that's leaving groupability. That's not all that fancy. We don't need that either. When we're talking about cyclic oxidative cleavage, what we're really putting an emphasis on is the breaking of the structure. And what makes structures in organic chemistry? Carbon. So we're talking about cyclic oxidative cleavage. We're talking about breaking the carbon-carbon bond. Okay? So the result is that I'm going to somehow break that bond so that it no longer exists. The problem with that is an imbalance of electrons within it. And so one of the things that it's going to do is the other part of that, that's the O in cyclic oxidative cleavage, is we want to oxidize. What does it mean to oxidize? Add more oxygens, okay? Sort of. It means add more oxygen bonds. That's it. That could mean more oxygens. Typically, it just means more bonds. Right now, I only have one bond between the carbon and the oxygen. So if I want to oxidize, what do I need?
Add another bond.
2 bonds. That is cyclic oxidative cleavage. That's it. Okay? Going back to that red structure starting with, okay, we'll make our final product orange so it doesn't stand out. We just get those. Did I specify a proper structure at my carbons? For the record, I accept both yes and no's as an answer, but I would like an answer. Okay, you're saying no. Why not? Why is that bad? Why does it not look right?
Oh, wait.
Shouldn't that? Say it again. Keep going. No.
I mean, you have wedges there, but there's not different things connected to it, so that's fucked up.
How many bonds should a carbon have?
4.
4. So if you're going to say I drew this wrong, you're saying I'm doing it wrong because I've only shown 2 bonds. There's 2 implied bonds. Okay? So if you said yes, it's drawn fine, they're implied hydrogens. Okay? I intentionally didn't draw them because I didn't want to make it even messier. Those things have 0 bearing on the overall reaction. I don't care what they are, they're just there. Those things could be ours. Okay? If they're hydrogens, or one of them is a hydrogen, what functional group do we end with? An aldehyde, because if that R group was a hydrogen, that still has to be present in the product, and we now have an aldehyde. Okay? So those aren't doing anything to the chemistry. There are hangers-on. So we don't need to be super hyper-focused on those. What we need to hyper-focus on is where the chemistry is happening, and then now start to overlay that back. So we go back over to here. When we run the periodate reaction, how many products did we get? 2. Do I have 2 different products?
No.
Why not?
They're the same thing.
Touche. Try again. No. Why did I? They aren't different, but I have 2 drawings. Why did I draw 2 drawings? Why do I need 2 things? My product has 2 carbons because my reactant has 2 carbons. I am producing 2 structures from my reactant. When? All the time with periodate reactions. That's how they work. They produce those 2 pieces by cleaving the structure apart. Why does that become important to us? If we now look at the question that's asked, how many structures do they give us as a product? 1. What does that mean?
You have to recombine.
What do I recombine it with?
The peroxidate? Oh, how do you,
Nope.
what do you call it? No.
That's irrelevant. I don't care what you call it.
Oh.
What do I recombine this with? This produces 2 things, right? They have to recombine with each other to go back to making the reactant. What do I recombine this with? Nope. And we know it's not the NaIO4 because when we look at the core chemistry, I have 2 carbon-oxygen structures. NaIO4 does not have carbon. It is therefore not relevant to finding what this combines with. Would you like me to draw it? Yeah. Let's make it a little bit more obvious on what it combines with. Combines with this. Why'd you laugh?
I don't know what it's called.
We don't care about what it's called. You don't need to name it. Where did that come from?
Just
It's not the starting material. I don't know what the starting material is.
take it from the end of the product.
Say that again. What do you mean?
Yeah, I mean, you got it from the product. I mean, it almost
This
looks like it.
almost looks... Oh, son of a bitch. Rewind back 30 seconds and pretend I drew that. Where did this come from?
The product.
It is the product. We produce 2 pieces. That does not mean they're different. And if I'm going to do a periodate reaction and it cleaves, and those 2 pieces are identical, why would I draw it twice? I'm flipping lazy. I don't want to draw it twice. I'm going to draw it once. If I'm going to reverse the reaction, I have to acknowledge I didn't make 1 molecule. I made billions upon billions of molecules. Okay? Now that I have both of those pieces, just like I have both of these pieces, can I reverse the process?
Yes.
What should be our starting material?
The two of those combined.
How do you combine them? I know I just erased it.
Oh, by the oxygen. Right. Shouldn't it be oxygen or by the carbon connected to that oxygen?
Connect two carbons together,
What two carbons together?
the ones that are attached to the oxygen.
And?
Remove the double bonds.
And?
Connect the two oxygens together.
No.
Add hydrogens to the oxygens.
You mean redraw the core flipped chemistry that we drew to begin? Yeah, that's it. What's the rest of that carbon blue structure? It's a hanger-on. I don't give a flying rat butt about any of it. Okay? All I care about is the core chemistry. It's the carbons and the oxygens. Okay? And all I'm doing is reversing back to that core chemistry. Okay? You're making a funny face. So we'll reveal, I think, why you're making the funny face. Everybody got that image drawn, or at least seared into their brain? Connect that. Assuming I didn't forget any flipping hydrogens again. And see, when we look at the solution, it looks exactly like what I drew. Does anybody think it looks exactly like what I drew?
Not exactly, but it is functionally, I think, the same.
It's exactly the same structure. What was different about it?
You drew it sin,
Whoop.
so it makes sense for the reaction, but that one kind of just some rotation. So
Maybe I'm drawing that right. Right, I think. Okay. Those structures are identical. Why don't I show it like the blue? I mean, the blue makes more sense with how it reacted. Why don't I show it like the blue? There's some steric hindrance within this structure. This looks like I'm putting these isopropyl groups, which you don't need to know the official name for, but those isopropyl groups really close to each other. Whereas in the drawing that they've drawn them away from each other. They've drawn the lowest energy conformation. When we look at any drawing for anything on a test or in homework, what you're going to look at is the lowest energy conformation. The lowest energy conformation is rarely the form that is doing the reaction. Why would that be the case?
Because it's trying to get to a lower energy state. That's the whole goal.
If it was low energy to begin with, should it react? No. Okay? But when you're processing through how to navigate where these pieces are moving and coming from, you should be looking at those higher energy drawings. That's your baseline. That's your practice. Find that core chemistry, revert it back as ugly as it looks. Yes, my blue structure looks awful. Okay? Once you've got it, now you can say, can I make it look pretty? Yeah, sure. I can make it look pretty, do some bond rotations, come into alignment, make it look like that. That's great. Okay? But don't worry about making things look pretty first. Make them look correct, then make them look pretty. Okay? Which becomes a challenge, because when you go through and look at the internet and you watch videos, what are the videos you're going to see?
Pretty.
They're going to show you the pretty stuff, because pretty stuff looks cooler. Okay? The pretty stuff isn't how the world functions. It's the ugly twits. Whatever direction I got to go. Maybe it's better to go that way. Okay? In any case, sorry. Everybody's like, why is he apologizing? I don't get it. Questions? Does that make sense?
Yeah, thank you.
Okay. You really have to lock in on what is that core chemistry. Where are those things changing? Okay? And if we even think back to the drawing I drew, the drawing that I provided looked ugly. Why? It didn't show that full octet. It didn't show those pieces. because those pieces are hangers on. I don't care about them. Focus on the core chemistry. Worry about the hangers on secondarily. Okay? Much easier said than done. We good? Cool. What's next?
Are you able to go over and analysis?
No.
And question 6 on the cyclic oxygen?
You took too long. You're welcome. Okay, maybe, well, let's see. Yep, you took too long. One of the videos that you're going to look at today, and that question was a nice segue. I will come back to you, I promise. Okay. There's this worksheet is found in the worksheet document. It's the synthesis worksheet. It's the synthesis MF edit online. Okay. And really what it's intended to be is kind of a game. Okay. Typically done with little playing cards, which I've got a bunch copied and printed out, and they look all nice and laminated, but they're in my office, so we can't use them for the game today. However, what we can do is we can use this game structure to help us kind of navigate this. So what I'm going to go through and do is I'm going to draw 2 reactions up on the board. Okay. I'm going to draw this first one. I don't know why it's first. It's the first one I'm drawing, that's why it's first. Okay. We've got 2 arrows. Sometimes you'll see them as half-ended arrows, it doesn't really matter. Usually I try and draw 3 for the record. Here. And here. Okay. What do those arrows mean?
Reaction?
Reaction. There's 2 arrows versus 3 arrows. Does the amount of arrows change the meaning?
Sort of.
Don't hedge your bets. Come in. Does it change the meaning?
I mean, that means there's 2 things reacting, 2 reactions happening.
Ah, okay, so we would assume that that means 2 reactions happening versus 3 reactions, versus 1 reaction, versus 4 reactions. Okay? These synthesis arrows do not mean that. They just mean some reactions need to happen. It could be 2, it could be 3, theoretically it could be 1, okay? It could be 20. There's some number of reactions that happen to make this conversion across. Right? So if we're going to look, I think I'm going to have to do it not recorded, so you'll just have to deal with it if you're watching from home. Because I am still recording. Yeah, oh well. Let's take a look at that first one. So CH3, we'll do this one together up on the board. We want to synthesize. Right? Officially, if we consider what you've learned in OChem 1 and kind of OChem 2 up to this point, is just a bunch of reactions. Just a bunch of reactions isn't useful. What we actually want to do is to be able to make something. Okay? So we want to be able to synthesize something. We want to say, if I start here, what could I make it into? That means doing a whole bunch of changes along the way. This is a concept we have to wait until second semester for, because we need to talk about the reactions that allow us to build larger structures and to move functionality. So you need substitution, elimination, and addition reactions at a minimum presented to you before you can deal with synthesis. Okay? Which, conveniently enough, guess what? We've reached that point. Okay? Which means now you have to start applying. It's not just what was the reactant for this reaction. It's now how many steps do I need to take to get from reactant to product? And that step means what are all the reagents that I need to navigate that? That's the end goal. That's a hard goal. Okay? It's an awesome goal. We want to get there. We won't. That's fine. Don't stress. Okay? But I want you to at least be thinking about that. Okay? Do I not have the directions on this? That would have been nice. It might be further back in my document. Can't see it. Okay, so I'll have to update the document so you can see it. So when we think about synthesis, what we need to be thinking about is where's the chemistry within our structures, okay, with whatever information we're given. Right? Typically, you're given a reactant and a product, and we want to say, what's the chemistry? So when I look at my reactant, where's the chemistry?
The pi bond.
Awesome, the pi bond. So this is where having multiple colors would really come in handy. Pretend that's red. Okay? And I also now want to look at my product and say, where's the chemistry? Pi bond. Pretend that's blue. Okay? We start with a pi bond, we end with a pi bond. What chemical reaction starts and ends with a pi bond? Good answer. None of them, that wasn't a chemical reaction. Right? Unless that pi bond has moved locations. Has our pi bond moved locations?
Yeah.
Yes. So now we're talking about a chemical reaction. Okay? We're talking about taking the pi bond within the ring and moving it to outside the ring. So now we can ask the question, what chemical reaction allows me to move a pi bond from one point to another point? Also a phenomenal answer. There isn't one. Okay? There's multiple. Okay? Because if I go through and look, this pi bond does not appear in my answer, which means what has to happen to this pi bond?
It has to go away.
It has to go away. So in the course of this reaction, I'm going to have to get rid of a pi bond. How do I get rid of pi bonds?
Elimination.
I have to do an elimination. Okay? No, try that again.
Addition.
Addition.
Oh, shit, my bad.
I followed the rabbit hole with you, so. I have to do an addition so that that pi bond disappears. What else do I have to do?
Elimination.
Now you can say it. An elimination to bring the pi bond back. Those are minimal reactions to process this. Right? I might have to add in more to facilitate those two core functional reactions. But now I know that those things need to happen. Okay? So at this point, I can do an addition.
Well, you need a reactant.
Okay. Now we run into a problem. How many addition reactants do you know? What was all that, Armand? I don't know any. Yeah, that's probably where you're at. Okay? You haven't memorized all of those reagents, so it's really hard to process that. But even then, okay, we just talked about cyclic oxidative cleavage. That's an addition reaction, because what did we do to the pi bond? We lost it. Would that be a useful addition reaction to run?
Not at all.
Not at all, because
It's no oxygen.
that my reagent can supply the oxygen. Why would we doing cyclic oxidative cleavage? You missed this part, I think. That's why. Not be useful reaction to run.
But you're cleaving it.
What am I cleaving?
The ring.
The ring. Do I want a ring?
Yes.
Yes. So that as an addition reagent was an awful reagent to pick. So it's not just what are all my addition reagents. Okay? I have to be selective about what I'm trying to do within those addition reagents. Okay? I have to know what target structure I want to get to. Because this as a target was a trash target. Okay? So it's not just what are the reagents and what are the targets, or what are the reagents. Now what are the reagents and what are the targets? If you don't know the reagents, what are the odds you know what target you're aiming for? Right? That becomes really, really challenging to process. That's the point of this activity. So what this activity has gone through and done is you see a whole bunch of ring structures. Ta-da, all of our answers had ring structures on it. Okay? A whole bunch of ring structures with varying functionalities associated with them. Okay? And if we look really carefully, we'll see some extra pieces of information. Okay? One of those pieces of information would be we have sets 1 and 2. Okay? Set 1 structures will apply to set 1 reactions. The reactions we drew up on the board came from
Step 1.
set 1. So we don't care about set 2, so we could zoom in a little bit more and make sure that set 2 disappears. Maybe. Can I zoom? Close enough. See, set 2's gone. Okay. What's the next thing we might notice about all of those structures?
All about oxygen.
False.
Oceans.
Yeah, say it again.
As our starting material and our ending material.
Our starting material and our ending material are in this set. So what we would do with the cards, or if you printed these out at home, is you would find the starting material and the product that matched our set. Ta-da, there it is. Right? We know we have to do these reactions because we looked for that chemistry, that functionality. We said what kind of chemical reactions needed to happen. Guess what those other structures are? Targets. They're possible targets along the way. So if we just talk about doing this addition reaction, we could now start being like, well, which of these targets would be a useful target? I wanted an addition reaction. Okay, here we go. F1. Okay. What happened to the pi bond? I lost it, and I gained 2 sigma bonds, which means I did addition. Do I know the reagent that allows me to do this addition? Now the question is shifted. It's not just what random targets am I going to. I have a target now, and now I have to think through that reagent list and be like, which of those reagents allows me to do this? Okay. And we can push on it a little bit more, because if we notice the changes here, yes, we have the loss of the pi bond, and if we talk about the 2 sigma that we gained, what were those 2 sigma? H and Br. Is there a reagent that would supply me H and Br? HBr, okay. How would that reaction work? What makes HBr reactive? It has a positive hydrogen. Which means what do I need to find in my carbon structure?
Negative.
A negative. Where do I have a negative?
One of them.
The pi bond. Cool. So I could now go through and say the pi bond could react with that hydrogen, sharing the electrons, which would then break the bond to the bromine. That's going to set me up with an intermediate. This isn't an intermediate. This is a target product along the way. So what we've done is said, here's a target, here's a reagent, let's test it. Let's test it and see if it works. Okay? So when we push that out, there's our hydrogen. We'd be like, oh, smart work. Ah, you aren't showing all about fine. Screw off, smart work. There it is. Okay? Okay? What else?
You'd have a positive carbocation.
I put the positive carbocation up there. I don't put the hydrogen up there because
It's
More
the most substituted position.
I want my carbocation to be at the most substituted position. Make it the most stable, lowest energy. Now what would happen?
The bromine would come in carbocation.
Bromine would come in, and that makes that product.
No.
No.
It makes that product. Is that what I was trying to get to?
No.
No. So what does that now mean?
That was bad.
What was bad?
The reactant.
Okay. If this is what I'm trying to aim for, this reactant sucks. Not going to do what I want it to do.
Or you could just change the target.
The target could move. Maybe this was a bad target. Okay? And if we dig into the reagents, does this target appear?
Yeah.
Yeah. Okay? So when we think through our reagents and what's happening within the chemistries, yes, it's important to recognize the overall reaction, but also consider where that's reactive. When I look at this starting pi bond, where's my chemistry? Yes, it's at the pi bond, but that pi bond is shared between 2 carbons, which means there are 2 reactive sites, those 2 carbons. If I look at my original target, I've changed chemistry at one of those. That makes sense. That's a reactive carbon. I could do that. I changed chemistry at the other one. That makes sense. I could do that. Do I have any chemistry at that position? And if I don't have any chemistry there, can I do that? No, that means that was a bad target to begin with. It moved too far as the chemical
Wouldn't
functionalities
that
go.
target be better for the other one up there?
It could be. Okay. And so our process is, how do we navigate this? Right? We start with just the reaction and we say, okay, let's slide a piece in. Do I think I can do this? Sure, this matches what I want. I want an addition, so that makes sense. So our first bet might be to eliminate I, H, G, yep, just those. Okay? And then look at the rest for possible solutions. We just said that we didn't like F, but we do like D. How about E?
No,
What's the problem with E?
it wouldn't get the pi bond where we want it, only do the elimination.
Ish. I mean, you're not wrong. Fucking pens.
There's a balloon.
I should not say that next to the freaking microphone. I should say that. My chemistry starts here, here, and it ends up here, right? Through the course of the reaction, where's my chemistry moving? Right? If we look at structure E, where's my chemistry moving? Down, it's going the complete opposite direction. That doesn't make sense. I want my chemistry to go up. So you can use those things to reason through those structures. Right? Does this mean whenever you do synthesis, you'll have a set of cards explaining what the... No, absolutely not. This is a step along the way, allowing you to start to think through how that chemistry can move and what makes logical sense for each of those steps along the way. Kind of, sort of? So, I said we'd solve this one, so let's solve it. HBr, lovely, I accept. That gets us to this guy. I want my elimination product. Can I do an elimination from this? What has to happen in an elimination?
You have to eliminate 2 sigmas and make a pi bond.
Loss of 2 sigma, okay, gain of the pi bond. And I extra like your phrasing on that ordering. The gain of the pi bond is almost an artifact of the loss of the 2 sigma. The loss of the 2 sigma is the more important feature. Okay, once those are gone, I can make the pi bond. Okay, so I have to get rid of 2 sigma bonds. Which bond in this structure do you think is likely to be gotten rid of?
Bromine.
Bromine, why?
It's more electronegative.
Awesome, it's more electronegative. I can expect those electrons to leave, which would leave what charge behind on the structure?
Positive.
Positive. To make the pi bond, what do I need? Electrons. I have to break another sigma. That other sigma is going to have to be what? A hydrogen, right? And ideally a hydrogen from out there, so that I can have the electrons swing in to make the pi bond. Okay? Is a carbon-hydrogen bond easy to make? Or sorry, break?
Not particularly.
No. Okay? It's an alkane bond, non-polar. Those are not easy bonds to break. Okay? If the bromine leaves, okay, is that reasonable? Would we expect the bromine to leave okay?
Yes.
Yeah, why?
Because it's large and it's more electronegative.
Large, more electronegatives, can stabilize itself, but what else gets left behind? What kind of positive? A tertiary carbocation. So we could actually see this just leaving on its own and forming the carbocation and the bromide chilling out here. Okay. Now to remove that hydrogen, that could make a little bit more sense because there's a reason to remove the hydrogen. It's not just let's form a negative carbon. It's let's stabilize the positive. Okay. What's going to cause that hydrogen to break off? Okay. Now it's thinking about our elimination reactions and what reagents do we typically add to make them work. Okay. There's 2 approaches. We have E1 and E2. The E1 forms a carbocation. It's kind of what we started talking about. Okay. But if we do the E1 and we add a base, ultimately it's a weak base because it's E1. Review. Okay. Where would we form our pi bond?
More substituted. So
E1 favors the more substituted product, which means it's going to reform the pi bond inside, taking us all the way back to the beginning. Which means, is the E1 mechanism the best approach? No. So I don't want to do E1, I want to do E2. The key differentiator between E1 and E2 is,
strong base.
there it is, base. So now what I want to add is I want to add a strong base. This strong base should remove the hydrogen simultaneous to the loss of the bromide. Okay? And when we run an E2, what elimination product is favored?
The least substitute.
It's the most substituted motherfucker. So how do we fix that?
Make it less substituted.
Is there a way to fix that? Because maybe you just say, yeah, that's it. I don't know. And if you say that, that's okay. That's time to go back and review our elimination reactions. When we talk about our elimination reactions, all of them favor most substituted, okay, known as Zaitsev's rule. And since we've named it, of course, what is there? An anti-Zaitsev's rule, also known as Hoffman.
Oh.
You can get a Hoffman elimination. To get a Hoffman elimination, what do you need? It's not just a strong base, because just a strong base like hydroxide is going to go to the most substituted and it's going to make it into this hydrogen. I want it to not react inside the structure. I want it to react outside the structure. So what kind of base would prevent it? What could I change about that base characteristic to make it harder for it to get to the inside?
Make it large.
Now I can say it's a bulky, strong base. Now I can say, what reagent do I know that matches the bulky, strong base? T-butoxide, T-buto minus. Right? That T-buto minus is going to preferentially remove the hydrogen from the outside. We skip the carbocation and we go immediately to that product. Zippity-doo-dah, isn't that exciting? You know what's extra exciting? It's time to get up. We got the boards.
Should we just go to whatever board?
Yep. We're looking at osmium tetroxide in the presence of a whole bunch of oxygen. I don't know why I said a whole bunch of oxygen. That's not really relevant. Okay. What is relevant? Osmium tetroxide, unfortunately, when I've seen OSO4, I've seen a whole variety of different things underneath that. Okay, and that what I've shown is the purple box. That purple box is technically necessary to complete the reaction. Sometimes it's implied, which is a crap way to do it, but implied in the statement of saying I have OSO4. Sometimes it's not. It's just going to depend on the question being asked. Unfortunately, all I can say is good luck. Okay? So what does OSO4 do? Okay? It's in the cyclic oxidative chapter. What it ends up doing is it reacts the oxygens with our non-polar pi bond. And we form this gross-looking structure. I'm going to ignore that for a second. Fine. Jiminy Christmas. Come on, pen. Just work with me. I only got like 2 minutes. Okay? And what's going to happen is we're going to get a new bond, whoops, to my osmium tetroxide.
Well,
Right? What?
I mean, with gross things, don't we break it? Or isn't that the whole point of this?
So, and this is, so where you're at within the cyclic oxidative chapter becomes challenging because this is going to be cyclic oxidative. It is not going to be cleavage. To get the cleavage, you would actually have to push to periodate. Okay? For this particular reagent. Okay? This is an unstable structure and it will fall apart. That's the purple box. Okay? Again, it is typically implied, so sometimes you see those extra reagents, sometimes you don't. Let's take a look at those red bonds. Okay? Those red bonds are chiral atoms, which means we need to specify the stereochemistry. As an extra hint that we need to be careful with stereochemistry, we can note that I have not drawn it yet, but will, that we started with stereochemistry in our starting material, which means we should be aware of it when drawing out our products. So let's go ahead and take a look at those red bonds. I, for whatever reason, like drawing wedges, so I'm going to make one of them wedged. What must the other one be? It also has to be wedged. There is no physical way I can get that to be wedged and the other one to be dashed with that small of a ring. Okay, I do have the possibility where it's also where they're both dashed. Okay, why do I get both those possibilities? Close enough.
P orbitals. Sorry.
P orbitals. We're talking about the alkene reacting, which is the electrons above or below. Both of those become potential products. Okay. What ends up happening is that that structure is unstable, and with a little bit of a push, that could be water in a small catalyst of acid. Okay, and that will finalize out to cleaving and leaving you with the syn diol. Okay? And you're like, that's crazy. I don't understand how that works. Welcome to the club. That's what it does. Okay? So the water somehow comes in, messes osmium, 76 on the periodic table. Dude, that's a freaking black box as far as we're concerned. Okay? So that's where we end. We would also have then the dashed conformation. Right? And when we go through to enter this into smart work, it would yell at us. Why do you think it yells at us for drawing both of these structures? Okay, it would yell at us because we didn't include the hydrogens. Fair point. So we fixed that. We're frustrated now, but fine. Okay, at least I eventually remembered that. We have to draw the hydrogens. Okay, now we enter it, and smart work tells us we're up.
Then one of the two must be better than the other in one way.
No.
Oh, yeah, so reacted with the stage 3.
Nope.
Smart work is an archaic system. It sucks.
Nope.
Well,
What is the difference between these two structures? They aren't enantiomers either.
they're the same.
They're identical. You just drew two of the exact same structure. SmartWorks going to freak out because it's like, why are you drawing something else?
It's like,
Okay, so you delete one and you're like, God, that was stupid mistake. Third attempt, whatever. I got it. Click. You're wrong.
Missing substituents.
Remember, I said I'd come back to it. That big old stuff that we had to worry about, the chirality at the other end. Did that change?
no.
No chemistry happened there, which means that chemistry is maintained. I should have that CH3. I already lost points on it already. Let's make sure we don't lose that stupid hydrogen. Our CH3, I'm drawing it at the wrong spot, but whatever. Our CH3 was wedged, yeah. There's my hydrogen. Wedged CH3. There's my hydrogen. Oh, but I'd be like, but they were the same, so I only need to draw one.
Now they're different.
Why are they now different?
Because you have the wedged methyl.
That wedged methyl did not also invert. We've lost our internal mirror plane, which means these two structures are not identical to each other. You would need to draw both. Oh my God. Okay, which brings in the last fun question that we'll just end this horrific day with. What is the relationship between the two structures? They are diastereomers. Okay. We mirrored two of the chiral atoms, which would suggest enantiomers, except we did not mirror the last one, which means the total relationship is diastereomers, which I think is also part of that question. You would have to check that. I think that's the second part, is what's the relationship between your drawings.
Oh, yeah.
Okay. So you would have to go through, make sure you show all those hydrogens, all that gory detail. Kind of, sorta? Can I delete it all? I mean, it's not permanently deleted. You just go to.
In what sane world would we be able to figure out like any of that first part? Just like on our own.
Just on your own? You wouldn't? Just on your own? How long would it take you to learn how to walk?
That's a good point.
How long would it take you to learn how to cut your hair? Brush your teeth? Take a dump without getting all the stuff stuck up on your butt. I mean, you are not by yourself. You are not expected to navigate it by yourself. You're expected to work through things and make reference to both your textbook and to me as a resource. Okay? Which I know absolutely is a scary concept. Like, I could never do this. You're not doing it on your own unless you make that choice. Please don't make that choice. I'll tell you right now, it's a very dumb choice. Don't do that. Right? You've relied on people throughout your entire life. Don't stop doing that. Realize that there are people here to help you, and we will, but we need to know to help you. We may suck at helping you, but we'll at least try. Okay? With that, we're done.